into this training program. Now we are going to treat of the selected example. We want to show you two virtual cases of design process going from large, let's say, scope to a much more focused scope on building. So we will take two examples of residential project, most likely, which are likely to be that, and then we will talk of the building block layout discussion, and then internal flows. So few things about the history and technology change and what is changed in this approach to cross ventilation strategies in terms of maybe architecture or general concerns. So I think things which are changing rapidly now is that there is an adoption of insulation in buildings in India, which was not the case before, which means that the heat ingress through the walls and roof is reducing. Then external movable shading systems, which are widely used in Central Europe, and allow reducing gain by about 85% of the solar gain through windows as compared to a single clear glass without shading. So definitely this kind of technology are likely to come and change a lot the scene of the building design. So which means also that to some extent there is more freedom to look at the building orientation, because the building orientation of facades become less important for the heat gains as compared to let's say old non-insulated buildings. And it gives more freedom to optimize the orientation of building to maximize the potential of wind-driven cross and also single-sided ventilation. So the concept for wind-driven ventilation can be developed further than only the conventional windward, leeward parameters, which are always the. So just to show you as a history, just some reminder of history of wind catchers. Wind catchers have been used maybe since the last 30th century in places like Iran or in Hyderabad, which was then part of the Indian continent. And they have been revisited. You can see here an example of a company called Monodraft, which is selling such kind of system, which are supposed to do a little bit the same thing as this Iranian typical wind catcher systems, but it remained essentially marginal because it's quite complex and not easy to put in place and would not provide sufficient air change as what is looked at in India. So typically, if we look at the conventional cross ventilation concepts, we can see that most of the things have been devoted to single buildings, in the sense that you think they are in a sense free. And you can see here a typical things from the well-known book, which was taken from Design with Climate, Victor Olgiai in the 1963, which was re-edited in 2015, but has not been changed at all. So if you think of this concept that it's windward, leeward, that means you need the pressure on one side, the pressure on the other side, negative, will give you the force to get cross ventilation. It is, of course, very difficult to apply in a dense urban context like we have in places like India. So there is a need to be able to analyze the urban issues for building layout and natural ventilation friendliness, so to say. So to come back to the different argument to develop such a software, it's not often possible to follow just the rule windward and leeward side as described in many of this passive design book. And there is a need to try to allow airflow to pass through projects around buildings more than it can happen if of the building are not placed properly. So it needs to think that maybe the cross ventilation may be also driven by the wind which is passing along the long facades and not directly hitting. And if also wind velocity is available above the buildings, one can develop strategy to create suction effect. So there are a few systematic studies. There are not many which have been, let's say, performed to a very detailed level. There is one very detailed study which has been performed in Hong Kong for a PhD, in the form of a PhD, called Natural Ventilation of High-Rise, High-Density Residential Building of Hong Kong. You have here the reference if you're interested. And I think this is, to me, the most detailed and comprehensive approach, going from let's say, district analysis down to buildings, and then down to flats even, and the design of the facade as well. So Vayu Pravah, in a sense, has been developed to contribute to this kind of revival of new approach of let's say, natural cross ventilation. So if you want to maximize the airflow across a district area, a project with buildings at meso level or at building level, comparing, the software has been a little bit sought for this kind of goals. So we can a priori study the impact of block building layout on airflow across an area of development. So you take into account local environment. This is a repetition, but I think it's important to realize what it means, the limits of the land plot. So in the example, we have shown that the limit of the land plot is respected also, even if we vary the geometry of the building. And then also, one can also use the software to allow predict what would happen if new buildings come around the project. And then we can develop compare strategies. And we are now going to go through two fictitious examples to illustrate the possibilities. So we are going to try to improve what is called the porosity, which means how much of the air which would pass through the building plot, the building land plot, the project, how much of it would go through. So this porosity is a notion which have been used now more recently in the urban designs, and which allowing the wind to pass through the city. So we'll take one example now where we look at the wind hitting in a perpendicularly the facade of the building, or almost parallel. Now on the base, we have taken, again, this is a schematic example, but to show the possibility that one can just highlight with the simulation. So if we have a building plot that could be a bar before the buildings that would come maybe later, representing other buildings. Then if we have good windward condition for the first row of buildings here, you can see that the other buildings, if you look at the colors, if you think that the blue dark is almost no wind and 3 meters per second is the dark red, you can see that you only have good velocity reaching or passing in between the buildings only for the first 2 rows, but there is absolutely no velocity between the buildings. So now if we try to play a little bit with the arrangement of building without changing the building themselves, neither in shape, neither in height, just to show, we can see here for the same condition of plot and the same simulation, you can see that the building which have been rotated and turned parallel to the wind with a longer facade, they are getting a much better wind velocity along the facades. So, and then this is another arrangement to show that it looks possible. Again, these are illustration. They are not real projects at the moment, because that will come with the users showing the use of the software later, and in the manual we will be preparing next year. So here, but you can see here that we are getting quite good velocity somehow. From 3 meters per second outside, we are keeping something like 1.5 at least between the buildings, which allows to imagine that you can have a better cross ventilation. Now, one of the main questions that people ask is that how do you do without doing very special and awkward architecture to catch the wind, which is passing essentially more in a linear parallel flow as to the facades. So here is an example which was developed recently in China on the research, where they have been looking at different window systems to see how they could impact the natural ventilation in even a single opening. And it's quite impressive how much this study shows the results which are possible without having fancy architectural tricks. So the principle is that we try here the schematic description of the example we're going to use, where by adding something which could be either a window open or a shutter or maybe a fin, or but not needed, then you can, with some velocity, you can transform the velocity into a pressure which generates a cross ventilation which is perpendicular to the wind direction. And then by this you can get a good cross ventilation, still having a good distribution of wind. So now if we go down to the building level, you can see here we have taken a zoom on 3 buildings only. And we see that even with a velocity of approximately 3 meters per second from far away, we are getting almost 2 meters per second at the entrance of some of the flats here. But we can see that the next one only has something like 0.4 or 0. So that means you are reducing. These buildings have hardly 1/5 of the airflow that the first one is getting. Now, if you change the orientation of the building, having the wind going along the facades and having this kind of special items to catch the wind, you can see that most of the flats have quite reasonable velocity of wind. And comparatively, you can see visually that the airflow is quite well distributed. It's not perfect, of course, but it gives an idea that if you have, let's say, adjustable component like window opening and stuff like this, people could adjust somehow their own cross ventilation by playing with the windows or shutters that you could have. So this is to tell something about what I call the porosity, which is that you allow the wind to pass at a greater speed in the domain of a district or project, and that increases significantly the potential because you have a massive amount of air that's passing through the project instead of being blocked by the first row of buildings. So which means the conventional windward, leeward is no more sufficient to assess, and that's why you need the software able to visualize the flow. And then clearly there is a need to develop more innovative, simple system which can just direct the wind into the buildings when having wind which are quite parallel to the long facade. So now we have another example, which is when you have wind above the building. Let's say if you have a dense square building project where they all have the same height, and then we see how we can change this. So here we have quite dense building with 24-meter height, 6-meter space, and 5 meters of wind velocity above the roof, a little bit more even. So when we look at this building, we have also a shield in front so that we think if new buildings would come, it will reduce even the wind that could come at a lower level. Now, if we look at the results of this, the windshield makes that there is hardly any velocity coming through the building. You see that the blue again is very, very low air velocity, but you have a high velocity above the roofs. But the problem is that you see that, like always in fluid mechanics, you can see that the boundary layer is always increasing, which means the low velocity is increasing with the wind passing along the buildings. So what we call it the detached flow. That means the high velocity flow is passing more and more far from the roof tops. So, and then if you use the threshold view, you can visualize that there is really a very low velocity between the buildings, and that there is very little air flowing between the buildings. So which means that cross ventilation just does not exist. So now the idea is, again, this is an illustration. It doesn't mean it's possible to do it this way, but is if you add one floor at each row of building from the wind, following the wind direction, then you are getting a much better wind velocity on the roof. And now so you have a velocity in the case of 5 meters per second at 10-meter height, you may get velocity on the range of 6-7 meters per second following almost the roof level. Now if we imagine that you have a courtyard, we'll see after how it looks like. If you think that this is the top of a courtyard or a shaft, vertical shaft inside the building, which is approximately 20%, 24% of the floor area, like so many courtyard can be, then you see that there is an impact on creating a negative pressure. And so now if we look more in detail, you can see that with the top courtyard, that is just mimic, it's a mimic here because we don't want to simulate all the building in detail to start with. So we just look at the impact and we can see that we are getting a negative pressure between 8 and 9 Pascal in this. And so after that, so we can see with the threshold, if we look at between 4.5 and 2.7 negative pressure, we can see that where we have placed the two courtyard top chimney, we see that there is this pocket of negative pressure that you don't get on the other one, on the other roof, which are not equipped. So now what we do is we go down to the building level of with the simulation. So coming from this building block approach, we go now to the building level and see if a building with a courtyard like this and having one floor where we consider internal flow, that means we have four, let's say four flats if one wants, which would have one opening in the facade and one opening on the courtyard. And if we look at similar condition of wind, what we can see is that the negative pressure in the courtyard is almost of 10 Pascal here. So which show that there is the simulation is only to demonstrate the feasibility of such an approach, but which show that you can really create a negative pressure, quite important if you have sufficient wind velocity, by using the velocity which is above the roof of the buildings. And by doing that, the courtyard with a raised chimney above the roof, it allows to extract the air that enters into the flats. You can see here the air going out. Of course, this is not, let's say, a final design. It is just to look at how this happens. And in case if the wind is not sufficient, there are also other things which have been tested where you could add, let's say, a fan system on top of the shaft, which is compatible with the passive mode, where you could reach 12 to 15 air chains. Sorry, there is a mistake here, with less than 2 watts per square meter. So this shaft approach can be also a kind of mixed mode or low energy assisted cross ventilation system, working with wind when there is a lot of wind and working with a fan or a fan system whenever it's needed. So this is the the view of the building which has been modeled. And this here you see this the view of the airflow around, and then again this negative pressure here. So thank you for your attention, and we are going, of course, to finalize a work which is already ongoing about a user guide with well worked out example to show how people can go through the process from, let's say, block level down to internal flows. So thank you for your attention.